Hey everyone, thank you so much for joining us this afternoon. I'm Philip from Base 10, and I'm going to be talking about high-performance inference for frontier AI models. Really quickly, we're going to cover a few things. We're going to cover the idea of inference engineering, the rise of open source foundation models, the components of an inference stack, including runtime performance optimization and infrastructure, and then look at what that does in production. So, I'm from Base 10. We like to say Base 10 is inference. We are an inference provider. We're in the AWS marketplace, and we serve open source, fine-tuned, and custom models on infrastructure that's purpose-built for production. We think about inference in a few different parts. Number one is performance. At the runtime level, you want to make sure that your actual GPU is utilized to its fullest extent to create the highest possible throughput at the lowest possible latency. On the infrastructure level, once you have that incredibly efficient model service, eventually you're going to have enough traffic that you're going to be saturating it. So you need to be able to scale horizontally to 2 replicas, 10 replicas, 100, 1,000 replicas across clusters and across regions. And then all of that needs to be wrapped in a delightful developer experience and delivered with hands-on support from expert forward deployed engineers. So, why did we build this? Why does all of this exist? It really starts with open source frontier AI models. And today, there are well over 2 million open source models on Hugging Face. This is up from just a few tens of thousands 4 or 5 years ago. And with these models, it's not just about the number, it's about the quality. Open source models are now routinely hitting frontier quality across different parameter sizes when you look at stuff like the Kimi K2 thinking model, or think back to January, DeepSeek R1, we see open source models finally crossing the gap versus closed models and delivering frontier intelligence. But it's not just for LLMs. They're doing this in voice. We have outstanding models for automatic speech recognition, for text-to-speech generation, for diarization. We have great image generation models from Flux and Stable Diffusion. We have models for generating and processing videos, as well as embedding models that can be used for all kinds of tasks on various data, including both text data and multimodal data. So with all of these different models, all at frontier quality, you need something that we call inference engineering. So inference engineering is the process of running AI models in production. And there are 3 principles that kind of define this engineering practice. The first is the idea that optimization requires constraints. So if we're going to optimize our system's performance, we need a goal that we're optimizing toward. We can't just try and make it better at everything. The second is that scale unlocks more performance techniques. If we're going to use something like large-scale parallelism, disaggregation, or other performance techniques, we're going to need enough traffic that we can cost-effectively leverage the hardware required to actually pull this off. And finally, we're going to need to stay dynamic. We're going to not configure our system one time statically and deploy it. We want our system to be able to update itself in real time to adjust to the different traffic configuration that's coming in from our live user base. And one thing I like to talk about to sort of illustrate these points is the idea of, I'm a big fan of the NFL. And one of the reasons that I like watching the NFL is you see those guys out there on the field, and they're big, they're fast, they're strong, and they're playing the sport. But they're not as big as sumo wrestlers. They're not as fast as Olympic sprinters. They're not as strong as a, say, champion powerlifter. And I think this is a useful lesson when it comes to inference optimization. Sometimes it's easy to get caught up in just trying to be number one on whatever benchmark. What really matters is making sure that you have the right mix of capabilities to actually serve the unique needs of your application. And a great example of someone who's really found that balance is open evidence. So the easiest way for me to explain open evidence is it's a chat application for doctors to be able to get up-to-date information. And so with they're a massively successful AI healthcare startup. And their CTO said about Base 10 that we support billions of custom and fine-tuned LLM calls per week for serving high-stakes medical information to healthcare providers at just about every major healthcare facility in the country. So how do you achieve this scale? How do you do that with this excellent performance and reliably enough to be used in a healthcare setting? So that really comes down to the idea of an inference stack. Again, inference is multiple parts. You need both the runtime component, you need to make sure that your individual GPU is working as well as possible, and you need the infrastructure component. You need to make sure that you can scale that optimized instance across many, many replicas. So let's start with the runtime layer. What does that look like? So inference runtime is really about applied research. There's all of these really interesting papers that are constantly getting published. You know, NeurIPS is in San Diego right now. There's a lot of really great research happening there. And the question is, how do you take these ideas from papers and actually apply them in production? So one of the major pieces of optimization technology that we use often is quantization. Quantization is the idea of moving from, say, like a 16-bit floating point number format down to 8 bits or 4 bits so that you can access higher power tensor cores as well as access or take better advantage of your memory bandwidth by sending less data with each pass through the model. So we think about quantization both in terms of being really selective with the formats we're using. I just gave a talk at NVIDIA's booth yesterday over there about everything we're doing with NVFP4, which is a new microscaling data format with Hopper, or with Blackwell. And then we also think carefully about what we quantize. Quantization isn't as simple as taking your entire model, chucking it in your model optimizer, and bringing out a quantized model. You want to think carefully about quantizing maybe just weights and activations. Maybe you can carefully quantize the KV cache to FP8. You probably want to leave attention alone. And even within these, within these neural networks, within each of these components, maybe you quantize only the middle layers and leave the input and output layers intact. So there's a lot of granularity that you can do in quantization to make sure that you preserve quality. Another main driver for us of performance is speculation, speculative decoding. You can use these different algorithms to generate draft tokens, which increases tokens per second on memory-bound decode. With every pass through the model, we can create more than one token, which is really promising. With speculation, we do a lot of different algorithms. Some of the ones that are seeing really great results right now are Eagle 3, which uses a sort of specialized trained model to do the speculation. The model takes hidden states from the target model and generates draft tokens. We also do a lot of look-ahead decoding, n-gram speculation, especially in the code completion field where you have a very constrained vocabulary. Another really important optimization for us is caching. We do a lot of KV cache-aware routing to ensure high hit rates on KV cache reuse. And with KV cache-aware routing, this is especially important for stuff like code completion. So a customer of ours, Zed, which is a IDE, was able to, with the base 10 inference stack, including a good deal of KV cache reuse, achieve 2x faster end-to-end code completion. So as you're typing, those suggestions pop up twice as fast, with a 45% lower P90 latency and 3.5 times faster or higher system throughput. So that's just one example of what these techniques can achieve. A couple other things we think about a lot are parallelism, especially with the rise of mixture of experts as the predominant architecture within large-scale language models. You have techniques like tensor and expert parallelism that need to be carefully balanced to ensure that you're making the right trade-offs between latency and throughput. And also with other modalities like video generation, which challenge even 8x B200 systems, you need approaches like context parallelism to ensure that you're able to split attention across these 8 GPUs and use all of your compute efficiently. And finally, one more runtime optimization I'm really excited about is disaggregation, where you separate prefill and decode onto separate workers that scale independently. This allows you to do a lot of these things I just talked about, as well as adopting different kernel strategies, different runtimes, and specialize each of your workers for the specific challenge of either compute-bound prefill or memory bandwidth-bound decode. So disaggregation, another thing supported by Dynamo, by the way, is another one of these model performance techniques that we've found a lot of interest in. But again, all of that together, I just went through 5 of the primary model performance techniques. Even if you do a world-class job of implementing those, that's not going to be enough for your production inference service. You also need the infrastructure to match that. And a big part of the infrastructure component is the idea of auto-scaling. So a lot of companies, especially companies that start out with large training clusters, end up with sort of fixed amounts of GPU capacity. The problem with fixed GPU capacity for inference is that traffic fluctuates. Maybe for business applications, it's highest during business hours, lower overnight, lower on the weekends. And when you have fluctuating traffic, maybe you're a consumer application, and sometimes you go viral on TikTok and get 1 million users overnight. Some days it's a lot quieter. In these cases, your static capacity is not going to be a great match for your traffic. When traffic is low, you're going to have wasted spend, and when traffic is high, even with all of these optimizations, your system won't have enough throughput. You'll start missing your SLAs. So that's where autoscaling comes in, to closely match the GPU capacity that you're provisioning at any given time to your traffic. At Base 10, we do a lot of traffic-based autoscaling decisions, and we're able to get this capacity via something that we call multi-cluster capacity management. While many inference services rely on only capacity within a single region, so let's say you're only in US East 1, you build your entire inference system there, with multi-cluster capacity management, you're able to pool compute across multiple regions, across multiple independent clusters, and with a single global control plane, treat it as a unified resource where you're able to, if you have, say, 10 replicas, schedule, 8 of them on one instance, 2 on the other. That gets you, great things like active-active reliability across regions, and make sure that you have access to both more capacity, more resilience, as well as more geographic proximity to your end users for globally distributed applications. And that matters because no matter how fast you make your model server, no matter how fast this bit is where the actual inference workload is running, if your network latency is slow because you're sending a request from, Singapore to California and back, or if your queue depth is high because you're waiting on, you only have 10 GPUs but you have 20 GPUs worth of traffic, no matter how fast this model services from that inference runtime layer we talked about earlier, your end-to-end inference time is going to suffer. So that's why it matters to do both the runtime and the infrastructure optimizations together to ensure great end-to-end latency. And another sort of customer who's experienced this is a company called Latent. Latent is a pharmaceutical search company, and they like to talk about how we save them a lot of stress and developer time in implementing highly reliable inference with this multi-cluster strategy and with these auto-scaling capabilities within the inference-optimized infrastructure. But everything I've talked about so far has been mostly focused on the idea of large language models. And I feel like large language models and AI are deservedly somewhat synonymous. But there's a lot of other modalities of open source models, like we were talking about at the beginning. There's image generation models, video generation, embedding models, text-to-speech, speech-to-text, and all sorts of novel modalities being developed today. So a great example of adapting this specific setup to a given modality is the idea of embedding inference. So embedding models take text as input and output vectors that encode the semantic meaning of that text. And I should say also there are multimodal embedding models that take images or videos and encode those similarly. So if you have this great capability around running language models, well, how do you then turn around and run embedding models? It turns out that embedding models, like many other modalities, are architecturally very, very similar to large language models. Most of the frontier quality embedding models today are stuff like Embedding Gemma, QuenEmbed, these models that are built out of open source large language models. As such, you can use the same runtime at the end here if you're able to build the rest of the system around it. Sort of a common theme in what I've been talking about with inference today. So for example, for based on embedding inference, you would have a model server sitting in front of it to process the requests, a multi-worker tokenizer that's able to take the generally hundreds or thousands of individual sentences or individual inputs that might be batched together in a single inference request to a embedding model in particular, stick it into a batch manager, queue it up, and have take advantage of the same sort of token by token in-flight batching, continuous batching mechanism that your runtime provides for language models. And then all of a sudden, you have the same high-quality inference service in a completely novel modality. So we've done this for embeddings, we've done this for speech to text, for text to speech, for image generation, for video generation. So all 6 major modalities of model that you could think of. And a customer of ours who's using this is Superhuman. You might know them as, they were recently acquired by Grammarly, who then themselves we branded as Superhuman. So Loic, he was the CTO of the original Superhuman email app. With this base 10 embedding inference, they were able to cut their P95 latency by 80% across tons of different fine-tuned embedding models that power key features in their app. And you'll notice one thing I like to highlight, I'm always proudest to highlight these P90, these P95, P99 latency gains, because they show the impact of this 2-part problem that I've been talking about all day up here, which is, it's not enough to be able to run fast, you need to be able to run fast reliably, and that comes not only from the runtime, but also from the infrastructure. So, to review, if you're going to build inference in production, you need to build 4 things. You need to deliver world-class performance, state-of-the-art performance in terms of time to first token, tokens per second, or whatever other metrics matter to you and your end users. You need to pair that with infrastructure that delivers 4 nines or better of reliability so that you can trust your applications for mission-critical deployments in fields like healthcare. You need to be able to scale GPU capacity across regions and maybe even across different VPCs so that you can handle, AI-powered applications are growing fast. We see customers routinely growing by multiples and multiples, compounding within a single year. And so you need to be able to very rapidly both scale on a month-to-month sort of global view. You need to be able to scale compute as well as individually within any given day. You need to be able to scale automatically up and down with traffic. And then finally, you need to be able to do that not just once, not just for one model, not just for one modality, but for any model, any of the 2 million open source models on Hugging Face, any fine-tuned model, any customized model that enterprises are increasingly turning to deliver differentiated value in production. All 4 of those things need to be done together. Thank you for the time today. I really enjoyed speaking with you. So we're going to be at booth 1632, which is like right over that way behind the Redis booth. We've got these artificially intelligent t-shirts. We've got a bunch of my teammates over there doing demos. If you have any questions whatsoever about the content that we talked about today, please join me over there. Thank you so much for your time.